students, welcome to Physics Lab. Today we are performing a new experiment, potentiometer. You have already learned in the theory part potentiometer, but now let's learn the concepts of potentiometer experiment. The main aim of the experiment is to find the EMF of the cell, to find the ratio of two EMFs of the two cells, and also to find the internal resistance of a cell. What is the meaning of potentiometer? Potentiometer means potentio is potential difference and meter is to measure. So it is used to find the potential difference. So let's learn first the construction of this potentiometer. It is a wire of few meters length, maximum up to 10 meter. But you cannot take the 10 meter length wire or a 5 meter length wire. It will occupy the space in the laboratory. So it is constructed in such a way that the space is safe. There is a wooden plank on which the wire is fixed. This is a wire 1 meter, 2 meter, 3 meter and 4 meter. So AB is a wire. Now you can see here this connection. There is a copper or a steel strip. You can understand it is a good conductor of electricity, and those strips are thick. Since they are thick, they have very low resistance. That means it may be almost zero. So then there is a connection here and there is a connection here. So this 1 meter is connected to this. So this is also 1 meter, 2 meter, 2 meter, 3 meter, 3 meter, and this is 4 meter. Now what is the material of the wire? Material is constantan or manganese. It is a metallic alloy. Now it has two characteristics. First thing, it has a very low temperature coefficient of resistance. What is the meaning of that? When you pass a current in the wire for a long time, the wire may get heated up. Now, the resistivity of the wire is also high. Resistivity rho, you already learned what is rho. It is also high. So it will not allow a large current to pass through it. And therefore, this material is used. So this is all about the construction. Now we'll start with the next part, that is how it is used. So start with the next part. There is this wire is a 4 meter length wire. So I draw a 4 meter length wire. Here, this is 4 meter wire, and it is connected to a standard cell or an eliminator. Here is the key and here is the rheostat. So this is the rheostat, this is the standard cell E, and here is the. Now this standard cell may have some internal resistance. Let's consider negligible internal resistance. We won't consider it. It is negligible. But if it is given, you have to also add that resistance in the circuit. Then we have a wire. This is my wire A point, B point. So these are the two binding screws of this wire. Now we are connecting the main cell. This main cell is eliminator. Now this is called as the primary circuit. It is called as the primary circuit. Now from the primary, suppose we put on this current. So the key is on. Current starts from here. Let us call this current is I. Flows from this wire. And then from here it comes back to the battery. So current is flowing in the wire. It is I in this wire. Now resistance of the wire. So this wire will have some resistance. Let us call it RAB. Then this wire has some length. Let us call that length as L. Though it is 4 meter, let us call it L, capital L. Now, we can find out the value, expression for current. Current we know from Ohm's law, total EMF upon total resistance in the circuit. The total EMF is E and total resistance is RAB plus RH. This resistance. So suppose by chance this is say 6 volts. Eliminator voltage is say 6 volts. So 2 volts is dropped here. How many volts? 2 volts is dropped across the rheostat. So what remaining voltage will be dropped here, that may be approximately 4 volts. It is 4 volts in fact. We will come to know about it. So 4 volts is dropped here. Now this is the current. After finding the current, there has to be some potential difference across this, because some potential drop is here. We call it VAB. It is equal to I into RAB, where this I you can substitute here. But we have to find out one beautiful expression for potential gradient. Let's see what it is. Now we already know current into RAB is rho into length is capital L upon area of cross section. Rho into length upon area of cross section is the resistance of a given wire. Now look here. Rho is what? Resistivity or specific resistance. What is L? Length of the wire. And what is A? Area of cross section of the wire. Now here the current which at one particular position of the rheostat, we say there is a constant current flowing through this wire, which is I. Now we can write this as VAB is equal to, now current is a constant. So current is constant, rho is a constant, and area of cross section is a constant. And therefore we can write I rho upon A. We can club it together, multiplied by L. So this is a constant called as potential gradient. This constant is called as potential gradient into L. So I rho upon A is the potential gradient. So if it is a constant, we can define potential gradient as VAB upon L. Now we come across a principle of a potentiometer. So what is the principle? When a constant current is flowing through a given potentiometer wire, then potential drop across any 2 points on this segment. So now supposing this is 4 volts. So here it is 0 potential difference. Let me divide this wire into 4 parts. This is 1 volt. This is 1 meter. This is 2 meter. This is say 3 meter. And this is 4 meter. Can you get it? So potential drop across any 2 points, of that wire is directly proportional. So we can write here V is directly proportional to length. So V is phi is a constant. So VAB is for L. So even at these 2 points, that voltage is directly proportional to the length of that segment. So what is the principle of a potentiometer? When a constant current flows through a potentiometer wire of uniform area of cross section and resistivity constant is of the same material, then potential difference across any 2 points of the wire is directly proportional to the length of that section of the wire. This is the principle of a potentiometer. Now let us perform the experiment to find out the potential gradient of this wire. Now this wire is 4 meter in length. Then this wire is I take a voltmeter. I go to the laboratory, I take a voltmeter, and there is a jockey. Here it's a plastic cover, and here there is a pointer which is steel, and we hold, and here we connect the wire. So this is a jockey. There is a jockey, and that jockey I just touch it here. When I touch here, at this point, the potential difference is 0 volt. Then I touch at 1 meter. Potential difference is 1 volt. It's shown on this at 1 meter. At 2 meter, it shows 2 volts. At 3 meter, it shows 3 volts. And at 4 meter, it shows 4 volts. So what is the meaning of that? Potential difference across AB is 4 volts. As I told you earlier, I kept the eliminator voltage as 6 volts. 2 volts is dropped across the rheostat at one position of the rheostat. So 6 minus 2 becomes 4 volts. So the remaining 4 volts is dropped here. We call that voltage as VAB. VAB is for 4 volts, 4 meter wire. It is dropped. Now how much it is? 4 volts for 4 meter. So VAB upon length, it is nothing but 4 upon 4. 4 volts upon 4 meter, which is 1 volt per meter. This is what we get. So at 1 meter, I get 1 volt. At 2 meter, I get 2 volts. 3 meter, I get 3 volts. At 4 meters, I get 4 volts. It is a potential difference across this length. So if I consider difference between two, here it is 2 volt, here it is 1 volt. So potential difference between two is 1 volt. This is the first part. So now we know very well, we have got a wire of potential gradient equal to 1 volt per meter. Let me put it in the bracket so that we will use it for reference. Now I thought of doing one experiment. Now our aim of the experiment is to find the unknown EMF, means EMF of this particular battery cell. Now this cell was a fresh cell 8 days back. What I did is I used it in my torch. I've used it for some time. Now I know that when it was fresh, it was 1.5 volt. After using it for some time, I don't know what is the EMF of the cell. Let us use this potentiometer to find the EMF of the cell. So what I am doing is, I am taking this cell, battery cell, whose EMF I don't know. So I call it E. And here, what I do is, I connect it to the galvanometer, and this galvanometer is connected to the jockey. This is my jockey. So this, I can move this jockey on this wire. Remember one thing, this wire now acts like a variable battery, because if I touch the jockey here, this wire has voltage equal to 4 volts. If I touch the jockey here, it has voltage equal to 3 volts. If I touch the jockey, not this one, I am just saying this wire is like a variable battery. Now what I do is, we are seeing what exactly happens in this wire. Before that, let us learn one. We have already learned a concept. I take two cells like this. Now you can see that these two cells get added up when they are connected in this way. We call them, the equivalent EMF across this is E1 plus E2, because they are assisting each other. Current is flowing in the same direction. If at all I take this cell like this is E1 and this is E2, then currents are going in the opposite direction. So total EMF is E1 difference E2. This is the first concept you need to remember. The second concept is, what I am doing is, I am using the same concept here. I take first part A. At point A, this is my battery. This is VAB battery. This is VAB, which is variable. And this is the EMF which I have to find out. EMF of this cell which I have to find out. And this is my galvanometer, and it is connected. This is the situation. So this wire is here, that battery, and this one is here. Now, at the moment, I take this jockey and touch at the A point. At point A. When I touch at the A point, potential difference is 0. You know very well. V at A is equal, potential difference at A is equal to 5 into L, and L is 0 here. 0. And therefore, potential difference at this point is 0. Let us call it 0. So, if this is 0, at this particular battery has a EMF which is definitely greater than 0. And therefore, this is a dominant cell, and the current starts flowing from here to here, like this. So, how the current flows? Current flows like this. So, the current flows from here, like this, it comes here and goes back. Have you got it? This is the way the current flows. Now, when that is the situation, this galvanometer pointer shows this side deflection. Now what I do, I take this jockey and I touch at this point, B. So at A, then at B. At B, I will just write here itself B, then the voltage is 4 volts. Voltage here, potential difference is 4 volts. So the current which is coming out is coming out in this direction, in the opposite direction. Current is in the opposite. How the current is flowing? It flows from B like this. So the current flows in this direction. Current flows in opposite direction. When the current flows in opposite direction like this galvanometer will show deflection on the right, full scale deflection on the right. This part is over. Now what I do, I take the third part of the story. Third part, I take this point I consider as say X. I consider this point as Y. Now, supposing I take this jockey and I touch at this point. 1 meter. And I find this is the situation. I find this is my 0 pointer. I get deflection somewhere here. It is from, that means how the current, who is dominant? Current is flowing from here to here, but this current which is flowing now is not a large current. It is a very, very small current because this voltage is 1 volt and this voltage is little greater than 1 volt because this pointer tells me that current is flowing in this direction on the left side. So this is dominant, but the current flowing is less. Now what I do, I take the jockey and slide it slightly, and at some position over here, I will call it the distance is 1.3 meter. At that point, I find that there is a 0 deflection. If I had to take the jockey on this side, I find that the deflection is on this side. Means it has increased. It is at 1.5 volts say. It is 1.5 meter. So the deflection is on the other side. And exactly at 1.3 meter, I get the deflection 0. That is the 0 deflection means null point. What is it called as? Null point. So there is no current flowing in this branch. In the secondary cell, there is no current flowing. Okay. Now, this point is a J point and the distance from A to J is 1.3 meter. That means VAJ, so 1.3 meter, at that point I get 0 deflection. What is the meaning of that? Potential difference across AJ, VAJ is equal to potential difference across this unknown EMF, that is the cell. So VAJ is here and this is the cell and the current is 0. That means this potential is equal to this potential. So potential VAJ is phi, that is the potential gradient, multiplied by 1.3 meter, which is equal to 1 volt per meter into 1.3 meter, which is 1.3 volt. Actually, it is obvious that when I touched the jockey here, I got deflection this way, slightly this way. This is my 0, here I've got. And when I touched the jockey at 1 volt, I got deflection here. That means my voltage of this cell is between 1 and 1.5 volts. That is the first thing. So now we have understood how to find the EMF of the cell, which is unknown to us. EMF is unknown to us, and accurately. Now think of the situation. This cell, which is unknown to me, this battery cell, which I have already, I want to find the EMF. I solder 2 wires here and connect it to the volt. Actually, I have done the experiment and found out. I connected to the voltmeter. You already know that it has got some internal resistance and connected to the voltmeter. And I find that the voltage here is slightly less than 1.3 volts. It's because if you see the total circuit, this E minus IR, I is the current flowing through it, R is the internal resistance, is equal to voltage. So some value is dropped across the internal resistance of the cell. Therefore, we get a slight lower voltage, negligible it is, but slightly lower voltage compared to what we got. So it is not 1.3 volts, it is less than that. That is one thing. Now we need to see two important points we have to learn. That is, we need to know what are the conditions so that this potentiometer will work. Point number one, this particular EMF has to be greater than this. That is understood. But it is not the only condition. Actually, the voltage across AB has to be greater than this. This is more important. Suppose I keep it 6 volts and the resistors of the wire and the resistor used at position, whole voltage is lost there, here. So that this voltage becomes less than 1.3 volts from here to here. Then we will not get the null point, we will not get the reading. And therefore, VAB should be greater than the cell EMF. This is the first condition. And the second condition is, you should not be connecting this way. If you connect negative to this positive, they will assist each other. And if they assist each other, means it will be like this, positive negative and negative positive. So they will assist each other, and if they assist each other, then we will not get a null point on the wire. This is not possible. We will solve some problems on this topic and we'll actually find out why it does not work. So remember these two conditions. Polarity is very important. So you must always connect both the positives of this eliminator as well as the cell at the A point. So these are the two conditions we need to know and perform the experiment. So now we need to perform an experiment, and remember one thing, stay tuned to the video which is coming up next. That is, we have to find EMF E1 upon E2. Thank you very much.